So let's try to do this in a general way now. All right, so we call this procedure Down Heapify. So let's talk about how we actually will build this. So I made a couple helper routines to help with the heap. So given a position I in the heap, left of I returns the position of the left child, right of I returns the position of the right child, parent of I returns the position of the parent. Root of I answers whether or not the node that we're talking about is a root, is the root. Leaf Li returns whether or not we're looking at a leaf of I. In other words, it has no children. And it has no children if where the right child would be is off the end of the list, and where the left child would be is off the end of the list. And then there's one other special kind of node, and there can be at most one of these in the whole tree, and that's a one-child node. So that happens if a node has a left child, which is the very last element in the array. So the right child just doesn't exist. So that just, well, and that's what I said. If the right child is at the very end of the list, then, or off the end of the list, then that's a one-child node. So Down Heapify is this notion that we've got we apply this in a notion where we've got a heap rooted at node I that satisfies the heap property, except perhaps I to its children, to its immediate children. So we can apply this if the heap property is satisfied everywhere except maybe between the root and its kids. So the root in particular, node I and its kids. Let's just say that. So if I is actually a leaf, then we're done, right? So we satisfy it everywhere except for between I and its children, and I doesn't have any children. So good. So that's great. Heap property is restored. If I has only one child, then we need to think a little harder. So in the case where I has one child, we check the heap property between I and its one child on the left. And if I is bigger than its child, that's bad. That means the heap property isn't satisfied. But all we have to do to fix it is we just swap the value in the left child and I. So that's what we did. And then now we know that that last node is the very last node in the tree. That node we just swapped into is the very last node in the tree. So it must be that things are happy everywhere. What if I has two children? So this is some internal node in the tree now, or possibly a root of a large tree. So we have to, now we check the heap property. So I'm going to do this way. I'm going to ask, look at the left and right children, look at the minimum value of those two. If the minimum value is bigger than or equal to L sub I, that means L sub I, the value at node I, is smaller than both the kids, so we're good. The heap property is satisfied everywhere. We can just return. On the other hand, sadly, if that doesn't hold, then we need to see which child is the smallest, or the smaller of the two, and swap I's value into that child. So that's just what we were doing in the example by hand. So let's check it. If the left child is smaller than the right child, that means that the left child is the smallest one. So we swap I and the left child's value, and then we need to down heapify on the left child. So we've basically fixed things everywhere except for possibly the tree rooted at left I could actually not satisfy the heap property. But that's okay. We can fix that by bubbling down the tree with Down Heapify once again. It's just what we did when we were doing it by hand. And then we can return. Finally, we reach this point if the heap property is violated and the right child of I it's between I and the right child of I. So we can just swap I and the right child of I, possibly causing the tree rooted at the right child of I to be violated. So we just run Down Heapify starting from there. When that's done, we can return, and we've established the heap property throughout the tree.